So we have just discussed the basic concepts of sensitivity of a detector. Next we talked about the response of the detector, right? Now let me again talk about the response. So response means we have to talk about the ordered pair, right? So X and Y, what will be the X? X is, say, energy of radiation, incoming radiation, and Y is basically the pulse height, the signal that is generated, the pulse and its height. Now we can keep on doing this, so on so forth. Let us take some numbers. Say for example 200. So what's the height? Say 1.1. Now it is very important, as students of experimental nuclear physics, you must know that normally the international convention is that whatever detector we use, the signals that we get, the signal is in volts, okay, and the range is 0 to 10 volt. So whatever signal you will be getting, you will get this within 0 to 10 volt. Okay, this is the international convention. Okay, so at 200, say keV, so this is say 200 keV. Say I am talking about gamma rays. Okay, gamma ray. The signal is around, peak height is 1.1 volts. Okay, say at 500, the pulse height is say around say 3.0 volt and so on. Okay, 500 kV. Now let me ask you a basic question. We can keep on doing this whole day. Suppose we have got, so basically what I am doing is we are selecting different gamma ray energies. So if this is my axis, say energy, okay, so I am basically choosing different energies and checking the pulse heights for each of them, okay, energy and checking the pulse height. Now the question is, suppose I have two gamma rays at the same time in the detector, so I will be expecting two different signals. Okay, say for this one, since the energy is this axis, see, so here the pulse height will be more since its energy is more. Okay, understood? Now suppose I am trying to put the two energies closer and closer. That means I am choosing two gamma ray energies which are very close to each other. Suppose, look what is happening here, they are almost close to each other. So the question is, will the detector always be able to identify two peaks separately, or there will come a time when the two signals, if they are very close, the detector will be unable to tell, and as a result of this we will get a single signal. So the question is this, will such a time come? The answer is yes. Okay, and why is yes? First we have to look. Students, very important, look closely. When I am talking about this energy, okay, for a particular energy, what am I getting? What should I get? What should I expect? Say for example, give me your 10 rupee note. He has got a 10 rupee note. Yes, so with this 10 rupee note, say, if I go to a shop and say, hey, give me candies. Say, candies normally 1 rupee. So how many candies will I get with this 10 rupee note? 10 candies. Now, have you ever heard that on Monday you go to the shop, he will give you 10 candies, on Tuesday he will give you 15 candies, on Wednesday he gives you 5 candies. Can you think anything like that? Same candy, it's not of different company. If such a thing happens, you will immediately tell the shopkeeper, what are you doing? You are scamming me? Do you take me for a fool? Now, but such a thing is happening in front of your eyes, but you haven't noticed. Look closely. Now, if this is the energy, the peak should be something like this, sharp, like a delta function. But what are we getting? Instead of this sharp stuff, what we are getting is not this, but we are getting basically see something like this. So instead of a single peak, I am getting a fluctuation. So if 500 kV is, suppose 500 kV signal energy is absorbed. So as a result of this, the signal I am getting, it has got a width. This is what I am saying. It's just like the same case. Of 10 rupee, I am getting 11, 12, 13, 8, 7 candies, something like this. So there is a fluctuation. Now, what is the reason for this fluctuation? The reason for this fluctuation is, remember what is happening. When the gamma ray or the ionizing radiation interacts with the material, what does it basically interact with? The atoms and ion, atoms, molecules and all that. And then we have ionization and the excitation, as a result of which electrical signals are produced. Now you see, this is a statistical process, the process of production of electrical signals as a result of ionization and excitation, because of which you see this number of ionization and excitation is not fixed. So it can happen that as a result of some gamma ray energy, say E, number of ionizations is say 1000. Next time when the same energy comes, the number of ionization becomes 1100. This is fluctuation, inherent fluctuation. This is a property of the detector. Just like your Heisenberg's uncertainty principle. You cannot do anything with it. It is there. Something like this. You have to remember. So because of this inherent fluctuation, we have got a width. Now, different materials will have different inherent fluctuations and they will have different width. There can be a material which will give something like this, a peak like this. Here, the fluctuation is very large. We will not choose something like this. Why? Because what we want is something like this. We want to answer this question. If we have two peaks close to each other, then should we be able to resolve them? Okay, this is what we want. We want a detector where as much, even if we have very closely lying gamma rays or peaks, we should be able to resolve them. This is what we want. So for this, we must have very narrow peaks. Very narrow peaks. You understand? Narrow peak. Now what is the peak look like? Peak looks like this. Last time we told you about the height of the peak. But this time I am talking about the narrowness of a peak, which is the width basically. Now a measure of this width is FWH. What is that? You take the maximum height, divide by 2 over here, and this measure is your full width at half maximum. So this is a measure of the energy resolution, and relative energy resolution for a peak of energy E is given by delta E by E. What is delta E? Delta E is this number, the width at half of it. So basically this entire concept of energy resolution means that if we have a gamma ray, say if suppose we have a detector, okay, let us have a detector where we know that at 1 MeV the energy resolution is 3 kV. What does this mean? This means that if we have two gamma rays, one is 1001 kV and another is 1002 kV, then the detector will not be able to resolve them. This is the meaning, students. Why? Because 1001 plus minus 3. What? 1001 plus 3 is 1004 and minus 3 is what? 998. Okay, so within this range, if there is anything, something like this, you expect that it will not be able to resolve. I am just giving an exact approximate number. Okay, so this is the region of your resolution, something like this. This is the importance of energy resolution. Normally students just do, hey, do you know energy resolution? Yes sir, delta E by E, delta E is FWHM and all that. This is how we measure. But the exact idea is coming from this. We want to measure as close as possible. Okay, this is the basic idea. So we must choose a detector which has very good energy resolution. Effectively, if you have a detector where these are very sharp lines, that's very good. Now, one of the best detectors out there is HPGE. This is basically the energy resolution of this high purity germanium detector. Approximately 2 to 3 kV at 1 mm. Okay. Now this also, what I mentioned, there can be fluctuations in this as well. Say 102 to 999. But overall, this is the range. Within this, you will not be able to resolve. This question might come in the examination. I will give you tell you about the energy resolution at 1 energy and ask you write 2 gamma rays where the detector will be able to resolve and 2 gamma rays where it will not be able to resolve. So in this case 1001, 1002 it will not be able to resolve, but 1001 and 1005 kV it will be able to resolve. Okay? Any questions regarding this? So look closely, this is 1000 kV, the energy resolution is your 3 kV, right? So basically 1000 plus 3 minus 3 region. Now if you consider half of it, so this is 1.5 kV, so let us take 2 kV. So 1000 kV plus 2 kV, so 1003 is barely resolvable, you can say. Similarly here, 997 is barely resolvable. Barely resolvable. Barely resolvable. But to be on the safe side, we will just consider plus minus 3 like this. Something like this. Okay?